Hello, this is a summary of the labs we did in AP Physics 2 on the 7th week of the 2020 school year during the COVID-19 crisis. It's about gas law labs, and it's a good kind of review for anyone who needs to think about the logic behind gas law labs. And I just want to show you guys what we did. So I had students use the University of Colorado PhET application, which allows you to relate volume, temperature, and pressure of a simulated gas, and it lets you look at what the molecules are doing. And I had students do a number of experiments. Ultimately, I had them pick an independent and dependent variable, and I had them see how changing one variable affected another. I asked them to do 3 separate experiments, one relating pressure and temperature, one relating volume and temperature, one relating pressure and volume. And students just picked which variables they were looking at and collected data points in this table. What we did in class, that was all before class, is I had students make a spreadsheet of their various data. So the first thing we're going to do today is use the spreadsheet to make graphs and try to find out the patterns, the relationships that these variables have. After we do that, we're going to combine them together into an equation, and then we're going to see how we might collect this data from real. So let's get started. The first step to making a graph in a spreadsheet, and I like Google Sheets for this purpose, so that's what this demo is going to use. You go to the graph insert function. Notice I've selected a cell that's not my data. I've noticed that Google Sheets is not great at picking out what data you want graphed, and none of the other spreadsheet programs are either. So I like to start with a blank slate. I go to Insert Chart, and now I'm going to add what my data says. Where Google Sheets says series, and Excel and LibreOffice use that same term, it means y-axis. So I'm going to collect my data that was, I want to go on the y-axis, which was pressure. I'm going to click OK. Now I'm going to do add x-axis. Annoying thing about Google Sheets as of October 2020, once you click add x-axis, you got to click this window thing, or else it'll bounce you out of the program. So there's all my x data. This bar graph isn't particularly helpful, so we'll change it from column chart to scatter plot. And that's a graph of pressure versus temperature. Since we're going to have multiple graphs, we should probably be clear about labeling. So if you go to Customize, Chart and Axis Titles, on my vertical axis, I had previously typed in pressure, and that's what I want there. You'll have to actually type that in. I was lucky it was already here. And on my horizontal axis, I'm going to type in temperature. But I already did that, so it was already loaded. So you go ahead and get your graph made like that. This looks pretty linear to me, but we're going to have the spreadsheet fit a line to see if that is in fact the case. You do that by going to Series under Customize, Trend Line. It does look linear, so I'll leave it like that. And I want to do Label Use Equation. So that's the relationship between pressure and temperature, according to that model that the University of Colorado put together. If you want to click Show R Squared, if you've had statistics, you know that this is a measure of how good the fit is. Otherwise, you can leave that out if you don't know what that means. But this really does appear to be a linear fit. The best fit line goes through all of these, and I'm comfortable saying there's a linear relationship between pressure and temperature. So we'll X out of here. We'll resize our graph, make it tiny, put it under the experiment. And I'm going to ask you guys to hit pause on this video and go again and make your data for the other two. So here's what that data looks like. And these two, I feel like we should be entirely comfortable saying that there's a linear relationship between pressure and temperature and between volume and temperature. This one should set off some alarm bells, both from how the graph looks with a linear fit and also what this would imply. So let's say for a second this is a linear fit, that leads to something very strange happening as you start to increase your volume. There's clearly a decreasing relationship. As you make the volume bigger, there's less collisions with the side of the container, so the pressure drops. That part makes sense. But if this was linear, something really weird happens. So let's pretend it was linear. What would it mean to have an x-intercept? Well, again, if pressure is because there's molecules colliding with the side of the container, as we increase the pressure, or increase the volume, there's going to be less collisions. We expect less and less pressure on the container. But we never expect zero. As the container starts to get bigger and bigger and bigger, those collisions will be less and less frequent. But the container would have to be infinitely big for the molecules to never hit. So we expect the pressure to approach zero, but not actually get there. The idea that there'd be negative pressure at some point, that doesn't make any sense. So I would say not linear. Big X. What would be a better idea? Maybe we have a pattern that has an asymptote. That as volume gets bigger, pressure drops and approaches zero but never gets there. And that's a more reasonable assumption. So a good choice of graph for this could be a hyperbola, y equals 1 over x. And in general, that graph would be y equals k over x. Some number k, some random number divided by x. And to make it specific for this graph, it would be pressure equals k over volume. So I want to see if I can fit a hyperbola to that data. It turns out that's not an option in most spreadsheet programs. So going back to my trend line, I don't really have a choice of hyperbolic. And this happens a lot with scientific data and even economic data and things like that. The equations we might come up to describe our models can be complex. So we have to have a way of calculating a regression that doesn't depend on it being a simple logical choice that a spreadsheet program gives us. So what we can do is we can do a process called linearization. And here's how linearization works. The first step is to make our equation so that the variables are in separate terms from anything else. So one of my variables, my dependent variable, is already alone, so I'll leave it there. My independent variable v is kind of combined with k here. So I'm just going to factor out the k. And I've got that. So to linearize, I then put the equation for a line, the classic y equals mx plus b, under the equation I've come up with. And now I'm going to see what I should put on a new graph on the y-axis and the x-axis. On the y-axis, I should put pressure. On the x-axis, I should put the inverse of volume. What am I left with? The slope apparently will be whatever that random number is. But because this new equation lines up with y equals mx plus b, assuming there's no intercept, this should be linear if I make a graph of pressure versus 1 over volume. So that's what I'm going to do. So on the original sheet I gave people, I had all these extra columns here. And if you were going to do this by hand, what you would do is you would do 1 divided by your first volume, right here. 1 divided by your second volume, 1 divided by your third volume. That's a massive pain in the butt. And I wouldn't actually ask students to do that by hand on anything other than a test. This is what spreadsheets were designed to do, to take routine work like that and automate it. So all you have to do to invert all of these, is to enter a formula into your spreadsheet. So what I'm going to do is make a new column, inverse volume, and that will be in 1 divided by inches cubed. Getting a little cubed from character note. And here's how you enter the formula. Equals tells the spreadsheet that this is a formula. And the formula we want is 1 divided by volume. 1 divided by. Then you click your first volume. Notice it didn't put 3.48, it put H4, the cell coordinate. If I go back up and look at the formula bar, 1 divided by H4 is there, and it knew to do 1 divided by the value of H4. Here's the magic. You take this little square, you hover over it, you get this crosshairs, you drag down. Boom. It does them all for you. Look at the formula bar. 1 divided by H10, H9, H8, H7, H6. It knows you want it to do all the ones next to it. So this is a really powerful way to do calculations and get lots of data points done at once. A business doesn't have to calculate percent sales tax on every single order. It doesn't have to calculate payroll tax on every single employee. You can enter a formula, drag it down, all that's done. Science, we use this to manipulate thousands of data points at once. So what I'm going to ask you to do now is make a graph of pressure versus 1 over volume, and we'll see if this actually fits a linear model. If it does, that shows that we were right, that there's an inverse relationship between pressure and volume. So if you do that, this is what you end up with, and you get a beautiful linear model. So there actually is an inverse relationship between pressure and volume. This is wrong. This is not, should not have a line fit to it, but this is correct. So at the end of the day, what you've got is 3 big ideas. Linear relationship between pressure and temperature. And we could say that that means pressure is some number times temperature, or that pressure divided by temperature is constant. That's called Gay-Lussac's law. Charles's law is the second one we did, the relationship between volume and temperature. So volume is directly proportional to temperature, or in other words, volume divided by temperature is constant. Boyle's law, the relationship between pressure and volume, that's what we just spent a lot of time talking about. Pressure is directly proportional to 1 over volume, which is another way of saying pressure times volume is constant. If you combine those ideas, which we've got here, you can make this one combination equation, that pressure times volume over temperature is constant. And that's what we turn into the ideal gas law. Pressure times volume is a constant times temperature. I just multiply both sides by T. What's in that constant? Students figured out using the PhET simulation that all their numbers changed if they put more gas molecules in. So it depends on the number of gas molecules, and there's still a constant there as well. So this is one form of the ideal gas law. It's not as commonly used. It depends on the number of molecules and a constant. Since most of the time we're dealing with gazillions of molecules, we find it more convenient to calculate the moles of gas that are present, and then use something called the ideal gas constant. And we left with this ideal gas equation, which relates pressure, volume, and temperature, and amount of gas. So we did this all in a simulated fashion, and I hope what you got out of it is that these three relationships are true, and that they're directly related to how individual molecules behave. As we raise temperature, molecules move faster. When there's more collisions with the side of the container, that's an increase in pressure. And I hope this gave you kind of an intuitive feel for what's going on. The last part of class, we talked about how we could actually carry out experiments on this. So what I did is I talked about giving students this device. So this device is a syringe that's sealed at the bottom with a set amount of air in it. I then let students stack textbooks on top of the syringe to change the pressure. And I asked students to come up with an experimental design that can test Boyle's law. So what does that look like? So Boyle's law is this relationship here. The relationship between pressure and volume. And I wanted to see two things. One, is there an inverse relationship? So in other words, is pressure proportional to some number times 1 over volume? And what we now know from the discussion we just had is that pressure is equal to nRT times 1 over volume. That's just from the ideal gas equation. So this sum number K should actually be the amount of gas, the ideal gas constant, and the temperature. The other question I had for students is, what is the ideal gas constant? So I asked students in Zoom breakout rooms to try to design an experiment that could answer those two questions. So the equipment I gave them in this experiment, I gave them the sealed syringe. I gave them all the Physics A textbooks their heart desired. I gave them a postal scale, which is good for measuring the weights of medium-sized objects like textbooks. I gave them a barometer. I gave them a thermometer. I gave them a ruler, a meter stick, and a stopwatch. And I asked them, with all that stuff, could they figure out an experiment to answer these two questions? So at the end of the day, some of these things are not needed. We don't need a stopwatch. We don't need a meter stick. But we do need to use all those other things. And let's talk about how. So the point of the postal scale is ultimately to get pressure. Measuring pressure requires two different sources of pressure to think about. We're going to put pressure on the syringe by putting more textbooks up there, and we can do that by figuring out what the weight of a textbook is. So that's one source of pressure. We then can convert that weight of a textbook into the gauge pressure caused by the textbook if we figure out the area that we're putting that weight on. And the area of the top of the syringe, basically, is the area in question here. So we divide the weight of the various books we have by the area of the syringe, which we can get by measuring the diameter of the syringe. And that gives us the pressure caused by the books. Now, because we're doing this on Earth, which is not in a vacuum, we have to think about what the absolute pressure is. What I just told you will get us to gauge pressure, but we have to also add in atmospheric pressure to get a total pressure. So at East Lyme High School, we have a weather station for the Davis WeatherLink network. So we have apps on our phones where we can get the exact pressure at our school at any time. So in the 2019-2020 school year when we did this, this was the pressure on the day we carried it out. Other variables we can measure temperature by just having a thermometer, and we can measure the volume by reading off the cubic centimeters that are in the syringe. So that lets us make a set of data. And what I did for students in order to collect data is I had them put down the number of textbooks. I had them read the volume off of the syringe as they put various books on top. One variable in the equation PV equals nRT that we have not talked about at all is N, the number of moles of gas. This is a constant in this experiment because we put the syringe top in, no gas is getting in or out. But I wanted them to try to find the ideal gas equation, and the ideal gas constant, excuse me. And without knowing the number of moles of gas in there to begin with, you can't really do that. So I don't know how you would do this in a high school setting in an accurate way to find the number of moles of gas you're putting in. I suspect one way to do this in a well-equipped chemistry lab would be to use stoichiometry, carry out some reaction that produces a certain number of moles of gas. So I did something that's totally cheating. I assumed the ideal gas constant is 0.0821 liter atmosphere mole Kelvin, and I calculated N using that. That is totally cheating. You can't use something in the process of discovery of that something because you don't know it. But I couldn't think of any other way to do the experiment. So if you can think of a better way, I would appreciate it. At the end of the day, I now have this data, which I've put into a spreadsheet. This is a different spreadsheet. This is Microsoft Excel. Works pretty similarly. So here's how we can transform this into a graph of pressure versus volume to check whether Boyle's law is accurate. I listed my number of textbooks. I got my volume in milliliters. I'm first going to turn number of textbooks into textbook weight by multiplying by the weight of one textbook, which I got using the postal scale. So that gave me my weight of textbooks. Then to get pressure, I'm going to divide the weight that was on top of the syringe by the area of the syringe, which I calculated having measured the diameter and using pi r squared. Notice that I've put little dollar signs in front of the J and the 7. That just tells Microsoft Excel that as I drag down, that I should always use this value and I shouldn't use any values below. So it's locking the spreadsheet on this value as the thing I'm dividing by. That gave me the gauge pressure in pascals, which I then converted to atmospheres, because that's the units we were going to use for this calculation, by dividing by that number. And then to get the absolute pressure, I added in the atmospheric pressure on the day we did this experiment. The last thing I had to do was convert from milliliters to liters, since we're using liters, atmospheres, moles, and Kelvin. So I divided all by milliliters or cubic centimeters by 1,000. And I'm left with that data. So if I were to now to graph pressure versus volume, column E versus column G, I should get a hyperbola. And since we've shown that this is an inverse relationship, I then inverted all my volumes. And that's what I'm ultimately going to graph. So this kind of goes through how to do this with Excel, which is a little different than Google Sheets. That's the equation I ended up So now, since the goal was to calculate the ideal gas constant, the slope of this line contains that information. So the last step is basically just to take the slope of that line and assume the slope of the line is n times r times t. And now I'll put in the number of moles of gas I cheated to get. I will set the slope of the line equal to moles of gas times r times the temperature that day, and I get a value for r, which is 0.0561. The percent error there is about 32%. It's not a well carried out experiment. This is why we started with those simulations to measure gas laws. Collecting this data is actually pretty tricky to do. You need pretty good equipment. You need to know exactly how many moles of gas you have, which I never could figure out. But I usually have students do this in class because I think just the experience of measuring all those different things and what you have to do to get these values is important for students. So obviously during the COVID crisis, this wasn't something we could do. So I hope the lesson we did in class helped. I hope this video helps for review. If you're watching this in any other school year, I hope this kind of gives you an idea of what students did in class if you missed that class. Let me know if you guys have questions. Thanks for all your work.